Friends, welcome to this channel Dr.ARM's Chemistry, and today we are going to discuss the part that is in continuation with the last lecture, that is bonding in organometallic compounds. So aromatic ligands and unsaturated ligands. Aromatic and unsaturated ligands. So we will come to know this point, that what is the effect of these aromatic ligands and unsaturated ligands on the strength of metal carbon bond in organometallic compounds. So this is our point of interest here. If we see that these compounds allows the pi contribution to the metal carbon sigma bond. So this is metal carbon sigma bond. So presence of such ligands here with this carbon shows that there is involvement of pi contributions between. So here the pi contributions are making use of metal d electrons and carbon p electrons, which are lying parallel to each other. So if we see here any example, that is, so here we find that metal d orbitals of pi nature, and here carbon p orbitals of pi nature, and here it is found that the d electrons of metal are shared with these pi star orbitals. For example, if we take the metal acetylides, so this can be represented as metal C triple bond CH. So this is metal acetylide, and because of this unsaturation, the metal carbon bond gets more stabilized than in case of the metal carbon bonds which are present in a saturated ligands. So pi contribution definitely adds to this metal carbon bond from this carbon, because metal provides d pi orbitals which are filled with electrons, and carbon has vacant p orbitals of pi nature. So this species is also isoelectronic with metal carbon monoxide, that is carbonyls. Since the charge distribution, here you will find that in these cases charge distribution is like this: metal possesses delta plus and carbon has delta minus. So this negative charge on carbon is stabilized because of pi bonding ligands, because of the presence of pi bonding ligands which are bonded with this metal. So this unsaturation, or the unsaturation present in aromatic compounds, means aromatic ligands like benzene, means the phenyl group. So this will help, that is to delocalize the negative charge. So the negative charge can be delocalized on the pi electron systems present in the ligands. As a result, the complex becomes more stable. So this delocalization of this negative charge of carbon on unsaturated or aromatic ligands. So this provides greater stability to the metal carbon bond as well as the organometallic compounds. Here we also find that this stability is also increased in case of stability is also found to be increasing in case of the ligands like metal, this CF3. Now means you can also consider here CCl3. So this CF3 means F and Cl are more or highly electronegative species, that is elements. So they have strong electron affinity. As a result of this, the electron cloud of carbon is drawn from this metal carbon region to this fluoride region of the atoms. As a result of this, the metal carbon bond is also highly stabilized. So such ligands are used to stabilize metal center in higher oxidation state. So this will help to stabilize the metal center in higher oxidation states. Thus, if we take the example of copper 3 ion, in case of such copper 3 ion, if we take the example of this copper 3 ion in CF3 4 minus. So this has a tetrahedral structure. This has a square planar structure. This has a square planar structure. And being the CF3, which are strong electron attracting groups, so this complex is found to be more stable. As a result of this, it can be isolated very easily, and the characterization of such compounds is also possible very readily. Similarly, the aryl groups, for example, in case of nickel 3, if we take this example of nickel Ni, the ligand is aromatic C6H54 minus. So here you will find that this electron withdrawing group, that is aryl group, gives more stability to the complex ion, and it has also square planar structure, and this has D7 methyline configuration, and this is 15 electron system, and that is why this complex ion can be easily isolated. Now we will go to the next part. This is part A, and now we will see the part B. That is, it is commonly found that the systems in which, systems means the organometallic compound in which the metal is bonded or coordinated to ligands where there is beta hydrogen. So we will see here what is the effect of presence of beta hydrogen or absence of beta hydrogen in the ligands, and what is its impact on the stability of that complex. So we will see here the effect of beta hydrogen on the stability of metal carbon bond. Metal carbon bond. So here the beta hydrogen means, if we see this is metal carbon bond. So here it is, the structure is like this. So here we will see this is hydrogen, means we will show it in some different way, that is like this. So if it is here any R groups, then this hydrogen after bond formation may come closer to this metal. As a result of this, we can get the structure in this way. So metal gets bonded with this hydrogen in this way, whereas we can have this carbon having structure like this. Here it is carbon, and this is the structure like this. So here metal gets closer to this beta hydrogen. So this is alpha hydrogen and this is beta hydrogen, carbon. So the hydrogen attached to this carbon is beta hydrogen. So this beta hydrogen comes easily closer to this metal, and there is interaction between this hydrogen and the metal. As a result of this, the bonds are broken and we get the metal hydrogen plus this metal hydride plus this structure like this. So you can get the structure in this way. So this reaction can also be considered in reverse form for the synthesis also, for the synthesis of these compounds also. So distinctly the presence of this beta hydrogen on beta carbon increases the stability of this compound, that is metal carbon bond, distinctly. So it gives stability. This compound, this carbon bond means metal carbon bond, or the compound gets more or distinctly stabilized. So equivalent to this, the other species are also providing stability, like the metal CH3 bond, then metal C, that is carbon CH2 C R CR3, or metal CH2 aromatic ring. Similarly, metal CH2 SiR3 SiR3, or metal CH2 NR2. So these are also giving better stability to the complexes. Then, so these are more stable than M. It is M here, MCH2 CHR2. In general, as well as the complex other examples, MCH2 CH3 means higher alkanes, higher alkyl groups are also showing less stability to the metal carbon bond or to these compounds containing metal carbon bond. So this effect is arising due to the presence of metal, this beta hydrogen, which forms the compounds after when metal comes closer to this hydrogen, it gets separated as NH, metal hydride plus this alkene. So the interaction of metal with this beta hydrogen is shown here. So this is about the effect of beta hydrogen. Now we will see the effect of double bonding and triple bonding. That is multiple bonding, metal carbon, multiple bonding, metal carbon, multiple bonding. That is double bonding and triple bonding. That is, you can show that this is metal carbon like this, or metal triple bond like this. So metal carbon double bonding or triple bonding. So these compounds are called carbenes, and these are called carbynes. So this is very interesting, and it shows that the effect is distinct. So if we see the example, one of the first example where this effect can be promptly observed. So the example is this CO5 tungsten complex Cr OMe. So here we can show this structure in this way in simplified form. OC5 metal, here is any metal, ONE. So if we see this example, so this shows that the crystal structure of this complex is competing with an octahedron. So we have shown only the part of this octahedron. So this has octahedral structure. And CO5, 5 carbon monoxides are occupying 5 corners of the regular octahedron, and sixth point of this octahedron is occupied by this double bond carbon and this species. So OMe CROME species. So here you will find that the bonding is like this. So if we consider here R, here when R is CH3 or C6H5, even R is like this, and the metal is chromium, then here you will find that the chromium carbon distance is 204 picometer. The distance is 204 picometer. And when this metal is tungsten, then the tungsten carbon bond distance is 205 picometer. 205 picometer. So this will show the effect of a presence of different metals. There is very small difference between the bond distance when the metal is chromium and when the metal is tungsten. If we see the bond distance in different species, when we consider the tungsten carbon bond, single bond is 205 picometer, which is greater than the tungsten carbon monoxide bond, which is 190 picometer, is greater. So here you will find that the bonding is formulated as here. If we see the tungsten carbon bond is sigma, plus there is a double bond, that is pi bond, and this pi bond is formed. This pi bond is formed by overlapping between the d orbitals of pi nature. That is, this p is formed by the overlap between the d orbitals of pi nature, that is dzx and dyz. dzx So if we take only for one pi bond, here we are considering only a double bonded structure. So here we will require only one pi bond. So this pi bond is formed by overlap between this dzx and carbon p orbital of pi nature, which is here shown as the vacant orbital, and this is antibonding. This may be also antibonding orbital depending upon the, but it is carbon p orbital of pi nature. In these molecules we are considering the dz as this z or z axis as the bonding axis, So here always we have to consider here z as a bonding axis. So this dzx orbital means here you will find that if we show these axes like this, which are perpendicular to each other. So if this is extended like this, So this is x-axis, so this is y-axis, and this is z-axis, like this. So the dzx orbital is lying between this z-axis and x-axis in this way, like this. Similarly, here x and this z-axis, like this. So there can be parallel p orbital of stable symmetry, that is symmetry. Similarly, the dy-z overlap would be used here for pi bonding. So instead of this dzx means z-axis, d x-axis, means instead of using this orbital between z-axis and x-axis, if we use the orbital lying between y-axis and z-axis like this, then also that we get the same result of double bonding. And these are giving the symmetrical, that is cylindrical symmetry around the metal, that is z-axis. So we get the cylindrical symmetry along this z-axis. So this is one of the important thing here. Now the z-axis and the Cr2 group, here the Cr2 group is free to rotate, and a range of metal carbines is known. Here. Now, if we consider another example, our family means range of these compounds, then we can get a variety of examples. Triple bonding. So we have seen by this time the double bond systems in multiple bonding. Now we will see here triple bonding. That is metal carbon triple bond systems. That is called, these are called carbines. Now these carbines will contain 1 sigma bond and 2 pi bonds. If we take the example, this I CO4, if we take this metal here is this tungsten carbon C6H5. So in this case and related compounds, the structure is octahedral. The structure is octahedral, and here generally we find that this iodine is trans. This halogen we will see in general, halide ligand is trans to the allyl group, trans to the allyl group, that is Cr, trans to the Cr, trans to Cr group, and the dimensions are like this. Dimensions here for R is equal to CH3, or or C6H5 and X is equal to F minus Cl minus or Br minus and I minus. Br minus and I minus. We can have the generalized example, means generalized in general we can represent the structure like this: X CO4 metal and this carbon alkyl group. So the structure of this is also represented like this: CO4 is metal and carbon R group and this halogen, that is X. In this structure, if for these compounds, when chromium, we use chromium, the chromium carbon distance is 169 pm. 169 pm. In case of tungsten carbon, the distance is 190 pm. The angle, bond angle, that is metal carbon R, is about 180 degrees. And if we consider the R as CH3, R is CH3 and C6H5, C6H5. Here this angle metal carbon R is equal to about, that is 170 degrees. 170 degrees. So this bond is expressed as an overlap. Here we can show the bonding, means there is a 1 sigma bond plus 2 pi bonds. So for this double bonding, we can have the overlap of metal with carbon, where carbon provides Px and Py, and metal provides the dxy, means dzx and dyz orbitals. So the overlap is between these orbitals. So this dzx and this x is here, the dzx is lying parallel to this orbital, that is px. Px is perpendicular to the bonding axis, and in this case dyz, the orbitals, these lobes are lying in the horizontal manner, and so that will form the pi bonding with these py orbitals, which are also present in the horizontal plane. So in addition to this sigma bond, we can have these two double bonds. So metal provides here px and py. So the pi contribution is available to this sigma bond from these combinations. Thus we can have three types of metal carbene compounds, where we can show the single bonds, double bonds and triple bonds. So these are comparable, means analogous to the carbon carbon sigma bond, carbon carbon double bond, or carbon carbon triple bond. So these are considered as metal carbon sigma bond, metal carbon double bond, and metal carbon triple bond. So these are the analogous examples. But compared to this, means if we compare this, these are stable, more stable than these. These means compared to these systems, these are weaker. Now, further, very widespread class involving metal carbon pi bonding is that unsaturated organic ligands bonding sidewise on to the metal. So this is seen in the carbines and carmines. That is sidewise overlap between metal and carbon on metal center. So these are, as we have seen just now, so these are called carbines and carmines. Complexes. So being these unsaturated compounds means there is a metal carbon double bond, triple bond. These are highly reactive. So these are highly reactive, and therefore they are used in number of reactions. Here the organic fragment which is highly reactive, that is carbene, carbynes, etc., is stabilized by coordination with the transition metal center. Here the highly stabilized species can be coordinated easily, and a wide and diverse range of stabilized entities are now established, including highly strained cyclic alkynes. Here we can have the highly strained cyclic alkynes. Such as cyclobutadiene, cyclohexane, cyclobutadiene, butadiene, cyclobutadiene, benzene, and trimethylmethane, So these are some examples. Now, inorganic entities are also stabilized here by these alkynes, that is carbines and carbynes. So, such as these are organic entities, and inorganic entities are the silylenes. Then the silylenes means R2Si, and the other Examples, corresponding examples are these germalenes, then stanylenes, So here metals are, here metal is Sn, that is tin, germanium and silicon. Metals are different. A major reason for this interest in metal carbon bonded species comes from the stabilization, which applies to the intermediates in many metal catalyzed organic reactions such as oxidation, that is oxo process. So these are applicable for oxo process, which are of industrial interest. Similarly, the Monsanto process, acetic acid process, and the Becker's process, So these compounds are finding numerous and industrial applications. So with this we will stop our discussion, but the point and topic is not yet over. So it will be continued in the next lecture also. So till then, goodbye, see you next time. But please do not forget to subscribe if not subscribed yet. And also please do not forget to press the like button. So thank you very much for watching this channel.